Speaker. Recently moved to McMaster University in Canada, and we're going to hear about the covariant-based constraint systems.
Okay, so, it's okay to start? Okay, great, thank you. I would like to thank the organizers for inviting me for this wonderful week of workshops. This is joint work with my student, Dori Lemelech, and his co-advisor, my colleague, Tomei Yarovich from the Department of Math. So let's get right to it. So constraint codes are often used both in storage and in communication systems, mainly to mitigate noise that occurs due to data-dependent issues. So in some cases, you have certain patterns or subsequences that are either offensive, hard to read, hard to synthesize, cause some faults in the detectors, and so on. And then we would like to avoid them, theoretically landing us in this zone of no noise whatsoever. But that is probably not really the case in the real world, and this only reduces data-dependent noise, maybe eliminating it altogether, but there's still data-independent noise that requires additional error-correcting capabilities. The question is, how do we connect the two? The specific motivation recently has been, once again, DNA storage, and thank you, Aidan, for laying the ground, reminding the audience about long homopolymer runs that are not good for DNA, both synthesis and reading, sequencing. GC content is a constraint that we would like to take care of, local weight constraints, and there are others. As opposed to data-dependent errors, we have data-independent errors, which are substitutions, insertions, deletions, burst errors, limited magnitude errors, whatever you would like. Yeah, there's like a ton of them. And I've collected at the bottom just a few very recent examples of papers trying to offer solutions that combine the two, namely codes that at the same time obey some constraint and allow us to correct a few errors in either of the models. Okay, so it's a mix and match, maybe a homopolymer runs with substitution errors and so on. So how do we actually combine the two? Well, we would like to maybe be lucky to construct an error-correcting code, all of whose code words obey the constraint. Now, this is generally very hard. Only a handful of ad hoc examples are known. During the recess before this talk, I was informed by Ido Tal over there that there is a way of combining polar codes with constraints. And there's also a non-constructive and very hard to compute lower bound on the rate of such combined codes given by Marcus and Roth way back in 92. Another option is to divide the problem into two sub-problems. Let's have an error-correcting code. Let's have a constraint code. And we have a box for each, like an encoder for that and an encoder for the other one. And then we somehow build a system combining the two. The two main ways of doing it are either concatenation or reverse concatenation, referring to whether we first encode the information using the error-correcting code encoder and then the constraint encoder, sending it to the channel, or we do it the other way around, first doing the constraint encoder and then the error-correcting code. There are many issues to be resolved. Both solutions are not really good. If you start with the ECC encoder and then do the constraint coding, then the sequence is going to be constrained. But on the other hand, on the other side, when you receive it, the first thing you need to do is to undo the constrained code. Namely, you need the constrained decoder. But since there's noise, this noise might be propagated sometimes with a limited range, and in bad cases, catastrophically, since most of them are designed using automatons with memory. If you do it the other way around, you first do the constraint code, and then you encode using the ECC, the resulting code word might not obey the constraint. And then when you send it over the channel, you might run into trouble. And there are ways of maybe doing only a systematic ECC, and then only having to care about the redundancy, and then maybe re-encode it, and then you really hope that it converges, and it doesn't always converge. There are a lot of trouble there. I would like to mention the state of the art. So there are works being published on this concatenation problem. I think the latest one is due to our friends in the audience. I don't see Ryan, but Eitan and Paul Siegel from 2018, ICT 2018, allowing for a correction of up to, so that's the best thing I know of, up to square root of n errors while maintaining a constraint, where n is the block length.
Maybe was this for a particular kind of constraint?
No, so this is very general. Our solution and also those papers mentioned here, except for the ad hoc at the top, are just general ways of combining the two encoders without knowledge of either of them. It's not tailored to any
So
specific
I
one.
meant like the square root of n has to be for a particular class of constraints or for.
I think it was for a general. Eitan, correct me. It was for a general any constraint. Okay, so what I'm about to suggest is a new way of concatenating. We call it Quantized-Constraint Concatenation, QCC for short, and it has nothing to do with quantum theory, even though there's a Q there. And here's the main message here. I will skip over most of the math due to time issues. So conventionally, in concatenation or reverse concatenation, the constrained word represents some data that you want to transmit and protect it against errors. And when you feed it into the constrained encoder, you expect to be able to reverse the process at the other end and undo the encoding, the constrained encoder, and get back the original word. But in QCC, we are going to look at the constrained encoder as a quantization process. Namely, we won't bother reversing it. And instead, we would, and therefore, by the way, we would not pay any rate for it. But instead, we will consider it as extra noise. So here's a summary with a block diagram. When we want to transmit a user code word, we take this U over here and put it into this ECC encoder, pick whichever one you want, I don't care. And then we get a code word. It's not constrained. It is capable of correcting errors, though, but it has no constraint on it. Then instead of putting it into a constrained encoder, which is reversible, we're just going to put it into a quantizer. So this quantizer outputs a vector x, a string x, of the same length as the code word, but it forces it to be constrained by introducing errors. Yeah? So the most common one I will be also mentioning further on is RLL. It's a common example. So RLL, let's say, is a 0K RLL binary, 0K RLL. Constraint is the set of all strings that do not contain a run of k plus 1 zeros. Okay. Okay, so this quantizer actually corrupts the code word. And then we put it into the channel, on the other side getting x prime because it is further corrupted by the channel. And then the ECC decoder, we don't have any decoder for the quantizer. The ECC decoder, for that one, attempts to correct the original code word. Now, how would that work? Well, the encoding is fine, but for the quantization part here, let us assume that we are not just randomly corrupting or forcing the output to be constrained, but we do so in a controlled manner. Namely, that this x that we have here is not too far away from the original code word C. So we would like to have maybe some bound on how many positions we had to change. If it's binary, let's say, how many bits did we have to flip in order to obtain this constraint? And then if on the other side we have this channel, if the total number of errors that we see on the other side, well, we have two sources of errors. One of them is the channel that we don't control, but the other one is the quantizer. If the total number of errors introduced is still manageable by the ECC, then we're fine. Okay, so let's see. If the channel does not introduce, okay, let's assume that the ECC code is capable of correcting T errors. Let's put some numbers on it, okay? And this quantizer here introduces, I don't know how, but at most R errors, then we have a budget of T minus R more errors that the channel may introduce, and we will still be fine. So the conclusion is that the error correction capability of this scheme depends on this bound R, this R here that is introduced by the quantizer. So as long as we can guarantee that for any string that enters this quantizer, we can force it to become constrained, not reversibly, by introducing no more than R errors, then we can calculate the rest of the properties of the scheme. But this is, well, we know this kind of, property. This is just what is called the covering radius of the constrained code. Now, funnily enough, covering radius has been studied for decades in the context of error correcting codes. So there are covering codes and their properties. It's good for compression. It's good for crypto. I mean, there's like a bunch of uses for it. But to the best of my knowledge, covering radius of constraint systems has not been studied at all. So now, do we go over the main hurdle, right? So the state of the art was a square root of n errors. Can we do this here? Well, let's assume that our covering radius, let's say normalized covering radius, converges to some, say, rho, which is between 0 and 1. So, and we have a code that is capable of correcting a fraction of delta errors. Then, in that case, we are left with codes, a total channel. I mean, we are capable of working with a channel that introduces at most a fraction of delta minus rho errors, which is theta of n. Now, well, that's nice, but do such codes exist? Well, trivially, yes. We just run the Gilbert-Varshavov bound, and if you plug in the parameters, as long as the covering radius of this constraint system is no more than half of 1 minus 1 over q, then it is possible to correct, to use an error correcting, to find an error correcting code with a rate that is non-vanishing. That rate would be this binary entropy, the Q entropy, sorry, of 2 delta. Okay, but there's no guarantee, right, that we can actually find something concrete. This is just an existence result, but at least we know that it is out there. So the scheme at least breaks this barrier of going over square root of n errors. Okay, so let's talk a little bit about the covering radius of constraint systems. So let x and y be constraint systems over some alphabet sigma. This radius that I was talking about, so here it's a slightly more general definition. So we are looking at taking all the balls of radius r centered at the constrained codewords of x and trying to cover all the constrained codewords of y. Now, we will take this and normalize it by n if we need, and take the limit as n goes to infinity to get this asymptotic covering radius, normalized covering radius. And typically, we would take y to be the entire space. We would like to cover everything and not just a specific subspace. But we get this for the same price, so why not just do it a bit more general? As an example, for the 0k RLL that I mentioned before, this is the set of all strings that do not contain run of length k plus 1 zeros. What is this covering radius? Well, we can evaluate it. We can easily see that we can force our way into becoming 0k RLL by taking any position that is a multiple of k plus 1 and forcing a 1 into it. And then we are sure to have no run of k plus 1 zeros at all. So that means we used a fraction of 1 over k plus 1. And if we look at what is in covering code terminology called a deep hole, if we look at the string of all zeros, this actually requires that fraction. So it turns out that taking the limits, we get that this covering radius is 1 over k plus 1. But here's something really strange happens. So for k, let's plug in k equals 1. That is, our 0, 1 RLL is just the set of all strings that do not contain two adjacent zeros. And we get that the covering radius is half, which is kind of a lot, right? So we need to, the budget we allow ourselves for covering is flipping at most half of the bits. Let's take another system, the repetition code, if you would like, that contains the all zeros or the all 1 vectors. Well, that one also has a covering radius of half, right? Because anytime you get a string, by flipping at most a half, you will get to either all zeros or all 1s. This is trivial. And so we get that we have two systems with covering radius 1/2, but one of them, the repetition code, has rate 0, whereas the other one has positive rate, meaning there are exponentially many strings here in this system. And even though we have this box with exponentially many points in it, if we want to cover the entire box, we would need a radius of 1/2. So that kind of tells us that those points are not evenly spread. The constrained codewords are not evenly spread in the space, are mainly bunched up in one area, leaving a deep hole, on the other hand, maybe, that requires a very large radius. So we're kind of paying for very rare patterns, like covering this all zero string. Can we somehow maybe do something, let's say, a little less extreme? The other concept I would like to mention is essential covering radius, which tells us, well, what happens if we allow ourselves to cover maybe 1 minus epsilon fraction of the space? Okay, so I'm giving myself a little bit of leeway here. And then we drop the bad patterns, and we lose a little bit of rate. But we will then take epsilon to 0 mathematically, and that would tell us essentially how much we need if we want to cover almost everything. So that means cover everything, let's say, with probability 1, if you wish. So again, with the definition, we have two constraint spaces, x and y. And now we need mu to be some invariant ergodic measure on y, and this constant epsilon. And once again, we're looking at the union of balls of radius r around the codewords of x. We're trying to cover all of y, so we're looking at the intersection. How much of y are we covering? And instead of just counting, we just take the measure. Okay. Now, again, this is way more general than we actually need, but we get it for free. We would typically take y to be the entire space. We would typically take this measure to be the uniform measure over the entire space. And then when we do this, the measure that I mentioned before is just counting how many of the strings of the space that we're covering. And so we are aiming to cover 1 minus epsilon fraction of the entire space. Once we do this, we get the same definitions before. We normalize by n for a given epsilon, which appears here at the subscript. And then we take the limit as n goes to infinity. But then we also take the limit as epsilon goes to 0, which essentially tells us the essential covering radius, how much of the space, how much radius we need to cover with high probability all of the space. So going back to the 0k RLL system, well, we will take y to be the entire space. We will take x to be the 0k constraint system, 0k RLL, and we'll take mu to be the uniform IID measure on y, just like I mentioned before. And the question is, did we gain something from this? By allowing this epsilonic leeway, do we gain something in the covering radius? Namely, we would like the covering radius to be smaller. Well, absolutely. The theorem that I will not have time to prove at all is that once you do this epsilonic, and even if you take epsilon to be 0, the covering radius becomes something like 1 over 2 to the k plus 2. Okay, let's forget about the -1 here, and compare it with the worst case combinatorial covering radius that absolutely under any circumstances has to cover the entire space, and then that is exponentially worse. It's just something like 1 over k. Okay, so in terms of the QCC system, what it tells us that if we use a combinatorial covering radius, we need the channel to introduce no more than this fraction of errors, delta minus 1 over k, approximately. Whereas if we take the essential covering approach, then we can get away with many more errors, a larger fraction of errors introduced by the channel. Okay, so to sum up, because I'm running out of time, I will mention a few of the results here. I mean, this work is just in its beginning. We can prove that mathematically the limit that we showed everywhere is just a limit, so we don't need to be too cautious there. And we can show a relation between the covering radius and the capacity, the combinatorial capacity of the constrained systems given here. And as for the essential covering radius, we can find an equivalent characterization of the essential covering radius using ergodic theory. And the definition actually allows us to bring into play nice machinery. So using simple, let's say, linear programs, we can compute bounds on the essential covering radius, which we suspect, I mean, in almost all cases, we see are actually the covering radius itself. So it's not just the bound, it is the actual covering radius, the essential covering radius. And, well, what's next? Well, there's quite a bit of work to do here. The algorithmic aspects of QCC are not complete yet. We would be happy to have a systematic way of building this box. So I showed you an example whereby we take any position that is with index a multiple of k plus 1 and just forcing a 1 into it. Well, that works for the combinatorial covering radius and for 0k RLL. But if we have a general constraint, we don't have a general way of building this quantizer, this box that forces strings that are input into it to become constrained on the other side, while maintaining a guarantee of how many bits or symbols we had to change. So a way of doing it that would be maybe like the equivalent of the state splitting algorithm that shows us a way of building an encoder that is reversible for constrained systems. The other thing is obviously studying the covering radii of well-known systems. We do know the solution for 0k RLL and for very simple cases, but even for dk RLL, we still don't know the covering radius. And we would like also to provide ways or methods for computing the covering radius for general constraints. So someone comes to me and gives me this graph representing a constraint. It's usually represented by a graph. How do I find out its covering radius? For the other side, computing its capacity, there's a well-known machinery through Perron-Frobenius theory. But for the covering radius, it's all new. We don't know how to do this. Okay, so with that, I would like to thank you for your attention.
Thank you. Also got us much closer back to on time, so we have time for a question or two.
Thanks for the nice talk. At the end, you mentioned, what was it? DKLLL? Was that?
DKRLL, so DK is the set of all strings that have between adjacent ones, you have at least D zeros and at most K zeros.
Ooh, okay.
Okay, so this is used in magnetic recording, optical recording, DNA storage, and so on, right? Because it controls the homopolymer runs that are we're trying to avoid.
It seems that it's a bit related to the error propagation of normal concatenation.
Okay.
Design concatenation with bounded error propagation. it may be similar ideas. So if there are schemes that attempt, that's maybe
The approach there is entirely different. So those bounding the error propagation is when you design a reversible encoder that has a state machine, and you want to design the state machine and its labeling so that you don't, the error does not take forever to resolve. But we're not trying to do anything reversible. So we are relaxing that part. You can do whatever crazy scheme you want, like forcing ones into positions. That's fine. So yeah, but maybe we'll take a look. That's a good idea.
So it is joint source and channel coding in some way.
If you want to label it like that, yeah, sure.
Mm-hmm. And then, does it make sense to think, for example, for lattice codes, this same approach?
Maybe. I haven't thought about it. Yeah, it sounds interesting. Okay, I can't say anything for sure, but yeah, that's an interesting idea.
I just have one comment. It's because you don't talk about this at all, but when you decode the final code, because the noise in the first part is a function of your message, right, you should be able to decode this much, much better than if it was random noise. There should be like a typical set decoder that does much, much better, right? Because
yeah, we have a lot of spare here. So what I kind of glanced over is the fact that I mentioned that this quantizer box gets any string and outputs something that is constrained, but I don't get any string. I get a code word. So yes, absolutely.
in a list decoder, for example, right, you could say which ones could have been, which is the most likely given the whole thing. And I imagine whatever rate you're losing doing this process, you can get most of it back. If you can build such a decoder.
That's an interesting idea. Yeah, well,
That's good. Good suggestion. All right, let's take the speaker.
thank you.
Maybe we'll just plan 45 as the normal. Maybe we'll have to come back in 50.